Continuing our discussion of bonding patterns in molecules, we're going to talk about the concept of resonance. Let's look at another example. We'll do O3 in this case, ozone. So this is the actual ozone, in the ozone layer or ozone action days. This is the molecule that's around. So still figure out the total number of valence. There's 3 of them, so there's 18 electrons here, and we want to figure out where they are. So I'm still gonna, even though it says it's O3, I'm still gonna follow the same idea. Put an oxygen atom in the middle and connect the other atoms, other oxygen atoms as my outer atoms. Okay, so I got that. I'm gonna do the same accounting process. I just used 4 electrons, so I have 14 left. I will go ahead and now put outer atom lone pair. So those 2 oxygens on the outside will get their 6 electrons that they need. They now have a full outer atom valence. Count for that, 12. Okay, so I have 2 electrons left. So I have somewhere to go. And so if I look, my central atom, oxygen, it needs electrons. So I'll put the lone pair there. I can do that. I can put those 2. But now I only have 6. So those 2 electrons helped, but I still don't have enough. So that central atom needs more electrons. So I can do the same thing I just did. I can convert a lone pair into a shared pair, make it a double bond. And so here's the Lewis structure for ozone. Oxygen atom in the middle as a single bond to one oxygen atom and a double bond to another oxygen atom. Perfect, I've got my Lewis structure. But one of the things I can ask is, why did I take the lone pair from the oxygen atom on the right? Why didn't I take it from the oxygen atom on the left? Right? That could have worked, and I could have ended up with this molecule, right? Where the oxygen has a double bond to the other atom, other oxygen, and a single bond to the one I just double bonded to. And does that work? Which one of those is better? Is there a preference there? What's going on here? And so both of these are plausible. There's nothing wrong with these, right? Either oxygen on the outside could be the double bond or the single bond. And so this is a phenomenon that's called resonance. And so resonance structures imply that there are more than one valid Lewis structures. When I say valid, I mean it's a Lewis structure where every atom obeys the octet rule. I've followed all of my rules for coming up with the Lewis structure. It's not just a random structure. I couldn't have something like this. I can't just connect to atoms however. It has to be 2 possibilities where basically I just have a different arrangement of electrons. The same types of atoms are bonded together. Maybe it's just a difference of double bonds versus single bonds. Okay, so for ozone, there are 2 of them. Either of these structures could represent the molecule. Okay, and so generally we represent these as we draw these arrows, this double-sided arrows between the 2 Lewis structures. And so we would say that either of these could work for ozone. So when it comes down to it, this is starting to run into one of the issues with Lewis structures. We would say here that there's a double bond between one pair of oxygens and a single bond between the other pair of oxygen atoms. And we know that those are different, right? One's shorter. We would say, according to this Lewis structure, that this is a shorter connection over here and this is a longer connection. But then in the other Lewis structure, it would be swapped. And that's not really going to work. And it is not the case that the molecule switches back and forth. The molecule is not going back and forth between, one double, one long, one short, one long, kind of, pumping or something like that. Instead, what happens is the real molecule is a mixture of these 2 Lewis structures, a mixture of these representations. There's this double bond on one side and single bond on the other. And so what ends up happening in ozone is it kind of has like a 1.5 bond, okay, that basically it's a share, half of it, it's kind of halfway between. It's a mixture of single bond and double bond. And we can look at that in terms of the properties. Oxygen double bonds are usually 121 picometers long, and a single bond is 146. And so ozone, the bonds are somewhere in between a single and a double, and so they end up being 128 picometers in length. So they're shorter than a single bond, but they're longer than a double bond. So their bond order is somewhere in between. And whenever we have this case where we can have a mixture of resonance structures, where there's these equally plausible resonance structures, in real life, they're always mixed together. Resonance in this case really does mean a mixture of these 2. And so sometimes you'll see these Lewis structures drawn with kind of this dashed line approach. That basically that dashed line implies that there could be a double bond here or there could be a double bond on the other side, kind of this half sort of extra bond. And so one of the things we can start to see from this is Lewis structures are only can get us so far. Lewis structures are really useful, and there's plenty of molecules that don't have resonance, and we can still understand what's going on here. But there's something more complicated. So we're going to start to see Lewis structures or use them. We're going to use them. There's a reason we learned about them. We're going to use them throughout chemistry to always draw molecules. But we do need to understand their limitations. And we're going to spend some time over the next couple weeks looking at more complicated descriptions of molecules to get at kind of what's really going on in these different systems. But, we have this idea there's a mixture. The thing we want to be important about with resonant structures, they don't switch between these. Instead, the real molecule is a single mixture of the two structures, or however many structures. Because we could look at something like nitrate, right? The first example we said was easy, right? We had a double bond over here, but we could have put the double bond right here or right here, right? It could have been anywhere. So in the case of nitrate, there are actually 3 resonant structures. The nitrogen can have a double bond to any one of the oxygens, and it can have a single bond to the other 2. And so as a result, you have 3 different structures. And again, these would imply different properties. These would imply that one of that double bond would always be shorter. But in a real nitrate molecule, all nitrogen-oxygen bond lengths are the exact same length. All 3 of them are this 130 picometers, kind of in between the double bond, triple bond length. It's some sort of intermediate bond. It's not as short as a double bond. It's not as long as a single bond. It's in between. So it's always going to be at that intermediate fashion. Okay. And so we know that that's always kind of going to be where it fit in. A resonance really means a mixture. There's always one bond length in the end, represented by a mixture of these different species. It's always going to be, the single structures, whether it's single bonds, double bonds, are always what's input into the mixture. So the Lewis structures are still useful. It's just, the real molecule is somewhere in between. So want to point out that, we can't, when we're talking about resonance, the bonds have to be the same. We can't just arbitrarily change our molecules. So these 2 molecules are both C3H6O. But they're not resonant structures. They look similar, but the important thing is that, in this case, the oxygen has a double bond to just carbon, whereas here it has bonds out there. So those are not resonant structures. These are just different compounds. They're related. They're very similar, but they're not resonant structures. In resonant structures, you can't change how atoms are linked together, just in terms of what other atoms is the oxygen bonded to. In this case, it's only carbon. Over here, it's carbon and oxygen. So it's not a resonant structure. You can change double, single bonds, but you can't change what it's bonded to. So we want to look at some more examples. How many resonant structures does carbonate have? So I came up with one Lewis structure for carbonate. This works for carbonate. What are the resonant structures? What else do I have for carbonate? And what I can always look for is basically, I put that double bond right there, right? I put it on kind of the bottom left. Well, it could have been on the top or it could have been on the bottom right. So overall, if I have a choice in how I form double bonds, that's always going to lead to the formation of resonance structures. And there's going to be 3 resonance structures for carbonate. So that indication that, I have that possibility of where I put the double bond is always a good formation of resonance structures. And however many choices I have is how many there's going to be. So again, in a carbonate molecule, it's really a mix of these. All carbon-oxygen bond lengths are going to be exactly the same because you could have the double bond on any of them, and it's really going to be in between all that double bond, single bond. All right, what about water? How many resonance structures does water have? Well, here, I don't have any choice. When I formed the Lewis structure of water, there was never a choice that I could make as to where I would put things. I just put in double bonds and single bonds. And so if we're talking about resonance, one of the key indications is going to be the presence of double or triple bonding. When we look at something like water, I don't have any flexibility. If I moved any of those electrons, it wouldn't have an octet anymore, right? Either oxygen or hydrogen would lose its octet. If I turned that bond into a lone pair on the oxygen, that would lead to the same thing as just breaking that bond, and I can't do that. So if I only have single bonds, I cannot have resonance structures. All right, benzene, C6H6 down there. How many resonance structures does this molecule have? And so double bonds is a good indication here, right? I got double bonds. And how could I move them around? And so I can see this is a pattern where I have this alternating pattern of single bonds and double bonds between carbon atoms. And so what I could end up doing is just swapping where the double bonds and single bonds are, right? This pattern of moving them one to the other. So basically I just moved all of them around and I made that nice kind of swap around over there. And so the important thing to note, again, since this is resonance, right? When each individual structure implies different bonding between carbons, but because I can make either of these rings, all carbon-carbon bonds are the same exact length. In between, the distance between carbon-carbon single bonds and carbon-carbon double bonds. They are always in between. It's a mixture. The real molecule is some sort of mix between these. It's a 50-50 mix, so you end up with half and half, and all of the lengths are exactly the same.